Okay, this video is from a tech talk that was given at the Treasure Lake Sportsman's Club ham radio group meeting, the annual or the monthly meeting, and it was held on November 8th, 2023. So the subject of this talk is um, specifically portable HF station batteries, and sometimes if you have a problem or a potential problem, uh, one of the things you need to figure out is, do I need to replace this thing and get a new one? And so I thought I'd go through the process I went through when I had a similar situation, and maybe you can use it in the future. To give you a little overview of what we're dealing with here, this is a picture of our portable HF station that Judy uses for Parks on the Air, and it is a Kenwood TS590SG mounted in a 19 rack mount portable gator box. There's a stereo headphone amplifier that is in there. She has a little hearing loss in one ear, and this helps her get a good balance of her hearing. And the whole idea here is that what you do is you pop the front and the back covers off, and most of the interconnections for the equipment is inside the box, and then you make the connections to the external equipment. For example, here's the foot switch connection. This is a USB port or cable that you would plug into the logging computer. There's another USB cable that we keep tucked in there, and what that is connected to is a SDR, an RSP1 SDR that we use for checking out the band scope if we need to do that. Headphones plug in here, and the Biennial battery plugs in here for the power. You can see we've got the fuses up here, and a little drawer for keeping notes and odds and ends in. And then on the back, just basically two connections. You bring the antenna into the antenna 1 port, and then there's a plug-in for the headphones, amplifier battery, and that's a small rechargeable lithium battery that we use so we don't put any additional load on the main radio batteries, because we could operate without the headphones if necessary, and I just want to reserve all the power we can from the biennial batteries, give us the maximum potential runtime. And the real reason for putting this box together was this connector right here. This is main power connector coming in to the radio, and it's not really made for repeated connections and disconnections, and we found we were getting some wear with that cable. So with this, we could just leave this plugged in, put our oh, I forgot to mention the power meters here. So we got the fuses of the power meter, and then plug the battery in here. So this is the only connection you need to make to the battery for powering up the unit. And this is the battery that we use, Biennial BLF 1215A. It's a 12 volt 15 amp hour battery, and we started with the POTA activations with a lead acid battery, deep draw marine type battery, 70 amp hours, and we ended up over discharging the battery beyond the recommended 50%. That is a guideline for the best long-term operation of a lead acid battery. And what was happening is that then when we over discharged it, when we recharged it, we had less run time than we had before, and then each time we did that, it seemed to shorten and shorten the capacity of the battery. So one thing we did is that we bought this battery. oops, and bought this battery here as a backup to the lead acid battery. And then when we decided to get away from the lead acid battery, we added 2 more identical batteries to it. So what that ended up is increasing our usable capacity over the 70 amp hour lead acid battery by about 30%, and we just start the POTA activation with one of the batteries until it runs down to 11 amp hours, and we'll get into why we selected 11 amp hours as the point to change the batteries a little later and switch to one of these other batteries. You can see we've got the power pole connectors here and a barrel connector for charging, and you can actually use this for powering something up too. In a pinch, you can plug this into the stereo amplifier as the battery, and then we keep the chargers in the bag, and then this is the small rechargeable battery for the headphone amplifier. So the problem we had is that during POTA activations, there was an intermittent catastrophe occurred, and when Judy's activating POTA, anything that keeps her from transmitting is a catastrophe. So what would happen is she'd be running along and doing just fine, and then without warning, the radio would shut down, requiring a restart of the radio and a restart of the logging program to identify the radio again. So there were 2 areas that were likely to be the problems. First area could be the battery. She reported it seemed to occur mostly on battery number 1, the oldest, but we never really nailed that down for sure. And battery 1 was the first one we had. At this point, it's probably had 100 to 200 cycles on it, but yet the specifications for the battery indicates that it should be over 1,000 cycles before we run into problems with that. So that was one of the problems. The other potential problem was a wiring issue. Maybe we had a problem with the wiring because we did use some cheap help in working on the wiring there. So you never know what happens when you get a loose nut doing your wiring for you. So what I needed was a way to test the battery, and so I could determine whether it was the battery or the wiring problem. Probably the straightforward way would have been to just dig into the wiring problem initially, and because that would be the most likely. But I really wanted to get a read on how the battery was performing at this point after operating it for over a year or so. So came up with a way that I could test the battery. So in order to get into how to test that battery, we'll take a look at some of the science and see what's going on here. If you recall back in the study groups, when we were working on our licenses, we'd look at circuits and use a water analogy for a little better understanding of what's going on in the circuit. And you might remember, for example, here if we had a tank of water, the height of the water would determine the water pressure in the system, and the water pressure is analogous to the voltage in an electrical circuit. And then as the water would flow, it would flow through a pipe like a wire. If there was a constriction in the pipe, that would be equivalent to a resistance in an electrical circuit, and it would restrict the flow of the water, and then there would be a pressure drop across that constriction. And then we would measure the volume of water passing through in terms of could be gallons per second or gallons per minute, just like we measure current in an electrical circuit as electric charge per unit time. So pretty good. Sometimes you can visually see what's going on with a water analogy, and it may not be quite as obvious in a circuit like this. So the thing to understand here is using the same type of water analogy is that the water capacity or the energy available in the water circuit is analogous to the amp hours in a battery. It's how much energy is in the battery or how much energy is in the water tank that can be used to do work, whether it's heating a resistor in an electric circuit or maybe turning a turbine in a water circuit. It's how much work you can get out of the device. So we're going to be using amp hours as a measurement of the energy to see how the battery performs as we charge and discharge the battery. So this is a curve, two curves of discharge curves for a lithium ion battery, the red one, and the lead acid. And in this particular example, this is a 56 volt battery. The magnitude doesn't really matter. It's the concept we're looking at here. And you can see with fully charged or zero discharge, this horizontal axis is the depth of discharge, we're at 56 volts. And then as we discharge the battery, pulling amp hours out of it, the battery voltage decreases. You get to 40%, 50%, it continues to decline. Not quite a linear function, but pretty much straight down at an angle there until you get to 100% and discharge, and then the battery's voltage is at its lowest value that it'll go. Now the lithium ion battery does a similar function, but the shape of the curve is different, and as one of the advantages of the lithium ion batteries is that as you discharge, the voltage, source voltage, stays higher and doesn't drop quite as quickly as the lead acid battery does, and it pretty much holds its voltage pretty tightly until you get out to about in this case, the 80% level of discharge. And then once you go past that, continuing to draw current out of the battery, it'll go over that knee, and then the battery voltage will drop pretty quickly. So the other thing to keep in mind on the lithium or the lead acid battery is this 50% discharge rate. Once you discharge the battery to this level, in order to ensure a longer term operation of the battery, you need to swap it out at that point, whereas you don't need to do that on the lithium ion battery until you're up here and right before you get to that knee. So right about this point is where you'd want to swap that battery out so you don't go off the rapid drop of voltage and can affect and wear the battery out somewhat. The other thing to consider in looking at, and you need to consider this when you're speccing out a battery, you're going to buy one, is a measurement called the charge rate or the C rate. And what that is just defined as a 1C rate or one charge rate will fully charge or discharge a battery in 1 hour. So if you look here at the blue line, this particular battery will be discharged in 1 hour, and you can see how the voltage on this axis will decline, and then here's that knee that we were talking about. If you charge or discharge the battery faster, say at 2C, so that would be discharged at half an hour, the drop in voltage is much quicker and by the time you get to the full discharge, your voltage is about where the other ones are, but through this range here, it's quite a bit lower than you would have if you were discharging at these rates. And the reason this is kind of important for this application of setting up a test is what we want to be able to do is to pretty closely approximate the discharge rate of the battery in the test to what it sees in the field when you're actually running the radio and discharging it at a somewhat constant rate, although it won't be completely constant because you'll be keying off and on the transceiver. So we need to pay attention to the discharge rate, or what kind of load we're putting on the battery in order to test it. Take a look at the battery information. I've highlighted the critical items in blue, and actually you should look at these from this perspective before you buy a battery too, to make sure that you have everything lined up. For the battery we use, it's rated spec is 12 volts, 15 amp hours, maximum continuous discharge current of 30 amps. So you need to make sure your electrical load consumes less than 30 amps. Maximum delivered power delivered to the load at 12 volts, 360 watts. It's just 12 volts times the 30 amps. And then looking at the battery capacity, it's a 15 amp hour at 13.8 volts DC. And the way I came up with the power consumption that I wanted to test at was that using that watt meter, I've noted what kind of average power levels Judy runs when she's transmitting, and she's pretty heavy on the transmit time. Typically, I think if you look it up, the single sideband usually runs at, say, 100 watt peak power. It'll average 25 to 40 watts. So Judy operates a little bit on the high side there. So I selected 40 watts as the average power estimate that we'd be using at the 100 watt setting. And then looking at the watts and the amp hours, or the amps, the life of the battery would be about 5 hours or so. And we kind of get around 4, I think it is, if we're careful, and swap it out at the 11 amp hour time. Then the other thing that we need to know is this value here, and what this is the lowest voltage that you can operate, and then at this point the radio will drop out. It'll protect itself by turning the radio off. And so we want to make sure that as that voltage comes down, as we're discharging the battery, we don't get to this point or even close to it. If we're right at say 11.8 volts, then we're probably too close to this lower level. Most radios, I believe, have circuits that will drop out the radio, turn it off if the voltage goes below or above this maximum. And the way to determine what the maximum and minimum voltage is if you look at the spec on the radio, and this is pretty typical of specs I've seen on different transceivers. The supply voltage is specified at 13.8 volts plus or minus 15%. So 13.8 plus 15% is 15.87 volts, so that'd be your upper limit. And then if you go to the minus 15%, you'd be at 11.73 volts. So we'll keep an eye on our readings relative to this value here. So the way I put this together is I took the battery number 1 in this case, and it's the BLF 1215A that we use. And then for safety's sake, put the fuse connection that we use in on the radio, And I didn't suspect this as a source of potential wiring problems because this was a commercially produced connection and fuse that we bought. So I was pretty sure that was okay, and we used it in this test with no problems. Then we have the PowerWorks watt meter, and I'll get into this a little more detail in a slide or two. And what that'll measure for us is the amps, the volts, the watts, the amp hours, the watt hours, the peak amps, the minimum voltage, and the peak watts. And we'll look and see how that works. And then used a fused cigarette lighter plug socket that would plug into the watt meter here. And along with that, I used a 200 watt DC to AC inverter. Now where this came from is that we have a camper that runs on batteries, and it also can run on 120 volts. You can get shore power to plug in, and we have two CPAP machines, so that if we don't have the shore power and are running exclusively off of batteries, I can plug this into the camper and plug the CPAP machines into this device, where we've got three 120 volt plugs that'll give you 200 watts. And just as this schematic symbol shows, what the inverter does is it takes the DC voltage and converts it to 120 volts AC. And then for the load, we got pretty sophisticated here and used a lamp. It has a lamp switch, and we put a 40 watt light bulb in there. And then this is a picture of the test setup. So there's the battery, the fuses. Oops, got to turn my laser on. The battery, the fuses. This is the watt meter, power meter, cigarette lighter socket. This is the inverter, and then we plug it into this lamp. And this is the battery case over here, just happened to be sitting there. So that was the test setup. And we take a look at this PowerWorks watt meter and power analyzer. And the way it's set up, it'll give you constant readings of amps, volts, and watts. And that's what these are right here, volts and watts. And then this part of the display will cycle through, step through the peak amps, the minimum voltage, the minimum watts, the watt hours, the amp hours, and the peak watts. So this amp hour is the reading that we use to monitor the discharge state of the battery. And when we're operating, it'll get to 11 amp hours, and we'll swap it out. And so it will cycle through, step through these like on about a 1 second interval. And then the way I took the reading for the minimum voltage, for example, is it would step through, and I'd watch about 6 minimum voltage readings. It'll say VM, and I'll note which one the minimum was of those 6, and that's what I recorded. That's what we were interested in, the minimum voltages. So the first thing I did is I plugged the, got everything hooked up, and with the inverter off and no load connected to the inverter, just the voltage to the inverter was 13.7 volts. And then when I turned the inverter on but had no load, I got about 0.28 amps at 13.66 volts. You can see the voltage drop just a hair. That's not much of a voltage drop. And then the power, the watt max, was 3.8 watts. So it was, this is kind of the overhead power that's consumed to operate this device. So that's not too bad. It ended up being, our target was 40. um, watts, and so this is the load from the inverter is about 10%, so 44 watts would be what we should have about hooked up. So then I set up a table, and I wanted to take measurements every 15 minutes. Set it up to go 4 hours because I knew we'd get to, or should get to the point of the 11 amp hours before about the time we got to 4 hours. And then every 15 minutes I'd record these values, the max amps, the minimum voltage, the wattage max, and the amp hours. And this last column, V limit, this is the limit voltage, the bottom limit that the radio drop out. So we want to make sure we can compare all of this information to that value to see how things are looking up. So we'll put this on a graph, and there it is. The axes, on the left-hand axis, you got volts DC. You can go 13.2 down to 11. On the right-hand vertical axis are amp hours. 15 is what the battery's rated for, so we've got that set up as 15. And then the horizontal axis is time, 15-minute increments. That's where we took our readings. And so the blue trace is the minimum voltage reading, and you can see it looks just like the one we looked at earlier, the graph, where over time, as we start drawing amp hours out of it, the voltage decreases as expected. And then we can look here at the amp hours, and as we start off at 0 here, and as we continue to draw power out of the, or actually current energy out of the battery, that accumulates, the total amp hours will accumulate until we get up to about here, which is 11 amp hours. And this is our planned termination point for the battery when we would swap it out. So you can see that what we have is at 11 amp hours, we're at about 12.4 volts, which is well above the green 11.7 volts that we need to stay away from. So that's good information. And I was able to reach the conclusion that there is no problem with battery number 1. We did find, or I found a bad crimp on one of the power pole connectors that guy did, and so I gave the guy 3 days off without pay, but Judy said forget that, get back to work. So I got back to work. So that's about it. I think that's the other point to make is that this isn't something you can use only for say a lithium or lead acid battery for a ham radio. You could, if you wanted to check a say you have a trolling motor or a cranking motor for your boat, or just any chargeable battery, you can set up the same type of display or same type of test if you understand what you have to where you need to be with the various settings. And this is how you go through and figure that out. The other thing I failed to mention was that watt hour meter is something that if you're operating portable on battery power or solar power or even generators, anything non-grid, I would highly recommend that you get one of those devices. I think they're around $50, and you can use it as you operate the radio, but you can also press it into service like this if you want to do an offline test to check out a battery. So it's a good piece of equipment to have. And I think that's about all I know. So 73, and this is K3SKS. Thank you.